Hi there. Today we're going to continue our lecture on neurons. Now we've already talked a little bit about some basics of cellular physiology and the properties of the membrane and basic ionic chemistry. And in the previous video we talked about the basic structure of neurons and sort of using their structure to learn some things about what they do. We also talked a little bit about glia. And in this lecture, really is maybe if I were to give it a different name, I would say what we're doing is we're getting ready to talk about one of the most fundamental functions of a neuron, or two of the most fundamental functions of neurons, which are the resting potential and the action potential. And just to kind of give you a little preview of what I mean here, I want to introduce these terms and ideas to you so that when we get into them in depth, you've already got some preparation. When we talk about the resting potential, what we're talking about is the fact that neurons at rest maintain an uneven distribution of ions between the inside of the cell and the outside of the cell. And so when we're going to talk about the resting potential, we're going to talk about how these ions get to where they are. And when we talk about the action potential, what we're talking about is the fact that when a neuron is excited, there is a rapid exchange of ions coming inside and outside of the cell across the cell membrane. And we're going to be talking about, when we talk about this in depth, we're going to be talking about what exactly triggers this rapid exchange of ions and how exactly this works. But before we can really dig into the guts of this and understand how this really works, there are some more basic concepts that we need to really be familiar with. And we're going to talk about those today. We're going to start off reviewing some very basic terminology having to do with electrical charge, voltage, current, and those sorts of things. For some of you, this may be review. For some of you, this may not. And we're actually going to talk just a little bit about how these things are actually measured in neurons, how we can actually measure the electrical properties of these living cells. So now the first two concepts that we need to talk about, and we've already discussed them a little bit, are the properties, or the two ideas are the ideas of electrical charge and the idea of ions. Charge, of course, is just a fundamental property of matter. Protons convey positive charge and electrons convey negative charge. Most of the time, atoms have an equal number of protons and electrons, which means they have a net neutral charge. But if they either gain electrons or lose electrons, then they become ions and they acquire a net charge. We've already talked about two different ions, chloride ions, which in neurons usually have a net negative charge, and sodium ions, which usually have a net positive charge. Later on, we're going to be talking about some other ions that have an important role in the resting potential and action potential, including potassium ions, which usually have a net charge of +1, and calcium ions, which usually come with a net charge of +2. The next idea that we need to be comfortable with is the idea of voltage. Before we get to voltage, one important property of charged particles is their properties of attraction and repulsion. And you guys, probably know this. Hopefully you have this from some of your physics background. Ions or particles that have different charges are attracted to one another. So a positive and a negative charged ions, they always attract each other. They want to come closer together. Like charges do the opposite. They repel. So two positive charges repel. They want to be farther apart from each other. And the same thing is true for negative charges. Two negative charges repel one another. Now, we can measure this property of attraction and repulsion through voltage. And voltage is simply a measure of the force that results, in particular, when two unlike charges are attracted to one another. So anytime you have a positive charge and a negative charge that are separated from one another, there's an electrostatic force which attracts them together, and the measure of that force is called voltage. Now, you may be familiar with the idea of voltage from the idea of just sort of household electrical current. So so one important thing we need to know about voltage is that when you measure it, you always need to measure it between 2 points. So for example, if you took this 9-volt battery here and you hooked a voltage measuring device up to the battery, if you attached one part of the device to this terminal of the battery and the other part of the device to that terminal of the battery, then what that voltage measuring device would tell you is that there is a voltage of 9 volts between these 2 points, and that's just simply a measure of the electrostatic force that exists between the 2 terminals of this battery. If we look at neurons, neurons maintain a net excess of negative charges inside of the cell compared to the outside of the cell. And if we measure the voltage between these 2 points, between the inside and the outside, then we would measure that voltage as negative 70 millivolts. So, the key idea here is that when we're measuring voltage, what we're really measuring here is the separation of charges between 2 different points and the sort of overall electrostatic force that is drawing those charges together. Now, if we imagine taking this battery and hooking a wire up to the one terminal of the battery and then connecting that same wire to the other terminal of the battery, what would happen is that the charged particles, because they're attracted to one another, would begin to flow through the wire from one side to the other. And anytime that electrical charges flow from one place to another, we call that current. Current is simply the flow of electrical charges that is driven by a voltage, driven by the separation of charges. And when current flows, it flows easily through, or I should say, when current can flow easily through a substance or a medium, we call that substance a conductor. So if we attached an electrical wire, as I said, to the terminals of this battery, current would flow easily through it because metal is a very good conductor. If we were to introduce a gap in this wire, let's say a vacuum or an air gap in this wire, then the current would no longer flow through the wire because air and a vacuum are insulators. So any substance through which that prevents the flow of current or resists the flow of current is usually called an insulator. All right, now what exactly does this have to do with neurons? Well, if we go and look at our cell membrane, what we'll see, first of all, is that the extracellular fluid, because it's an aqueous medium, because it's sort of a salty liquid medium, extracellular fluid is a good conductor. That means that charged particles, current, can easily flow through the extracellular fluid. The same is true of the intracellular fluid. Intracellular fluid, cytoplasm, is just, a salty aqueous environment. Current, charged particles can flow easily through intracellular fluid. So both the extracellular and intracellular mediums are conductors. They conduct current. In contrast, if we look at the membrane, and particularly these fatty lipid tails here, the membrane is an insulator. Charged particles or current, do not flow easily through the membrane. Now, this is going to be important later on when we talk about the separation of charges across the membrane and, in some cases, how charges can flow across the membrane through channels and pumps. All right, so, I said a moment ago that it was possible to actually measure the voltage that exists between any 2 points that have a separation of charge. And you could imagine it's pretty easy to hook a voltage measuring device up to a battery like this. But how on earth do we actually measure these things in neurons? And I'm going to just tell you very briefly about how we actually do this in real neurons and in real neural tissue. So in general, the way that we do this is through microelectrodes. So remember, as I said, neurons maintain an excess of negative charge inside relative to the outside of the cell. And if we want to measure this, what we can do is we can take a very, very thin, very sharp electrode, and it can consist either of a glass tube that's filled with a conducting fluid and that has an open tip so that the inside of the cell becomes continuous with the fluid inside the electrode. We can also use a metal wire that is insulated except for at the very tip. And so again, this allows there to be some electrical continuity between the inside of the cell and the metal part of the wire. We then hook this wire up to a voltage measuring device. And remember, we have one part of our voltage measuring device that is coupled to the inside of the cell, and another one that is somewhere on the outside of the cell. And we measure the difference in voltage between these 2 points. And again, when we're measuring a healthy neuron at rest, that difference is about -70 millivolts. Now, up until now, I've been kind of vague about what exactly this voltage measuring device is. There are many different ways of measuring voltage in neurons. One of the simplest and most common ones, one that's been used for many, many years, is called an oscilloscope. An oscilloscope is just basically a device that measures voltage over time. So I want you to imagine if we had a setup here with with an electrode hooked up to an oscilloscope, and at the beginning, if we kept the electrode outside of the cell, well, what that would mean is that we'd be measuring the difference in voltage between this part of the extracellular fluid and this other part of the extracellular medium. And because we would be doing this in an aqueous medium, it would be a medium that current flows easily through. And what that means is that there would really be no difference in charge, no net difference in electrical charge between the one part of the extracellular fluid and the other part of the extracellular fluid. So at the very beginning, if we keep that electrode outside of the neuron, we're going to measure a voltage of 0. If then we imagine we take this electrode and we insert it into the neuron very, very quickly, what we would see on our oscilloscope is we would see the voltage immediately drop down to about -70. And that's because, as I mentioned before, inside a neuron there is an excess, a net excess of negative charge inside of that cell. And what the oscilloscope is measuring here is quantifying that difference in charge between the inside and the outside of the cell. And as I said, in most neurons at rest, this is around -70 millivolts. Now, if any of you guys ever go into research, you'll learn how to use these devices. But I just wanted to kind of give you a little insight here into how practically you can actually measure these things. Yes, of course. And I forgot to mention one of the most important parts. So let's say you did this little experiment and you stuck this electrode inside the cell. If you were patient and you waited a while, or maybe even if you stimulated that cell a little bit, what you would see after a while is that this -70 millivolts would occasionally be interrupted by this rapid increase in voltage going up above 0 into positive territory, meaning that there's very briefly a net positive charge inside the cell, and then just as quickly going right back down again to -70. This brief jump and drop in voltage is called the action potential. As we're going to see, this is the main sort of signal that neurons use to communicate with one another. And we're going to talk a lot about this. We're going to talk about how the action potential is generated. We're going to be talked about how it's used in the transmission of information from one neuron to the next. But just experimentally, we can use an oscilloscope not just to measure the resting potential, but we can also use it to measure the presence of action potentials. All right. So for this portion of this, I just kind of want to walk you guys through a little bit of a thought experiment just to help you kind of understand kind of maybe how all of these parts fit together. So the setup is this. So let's just imagine that you had a cell, and this could actually be any cell. It doesn't have to be, wouldn't have to be a neuron, but let's say you had a cell here. This is our cell membrane, so which means this is the inside of the cell and this is the outside of the cell. And let's just imagine that we had a cell with an equal number of positive and negative charges inside the cell and an equal number of positive and negative charges outside of the cell as well. So imagine if we hooked up a voltage measuring device, and we put one part of the device inside the cell and another part of the device outside of the cell. And so in this instance, what is the voltage that we would measure? What's the separation of charge that we would measure? Now this is an easy one. I just told you that there is an equal number of cell positive and negative charges inside and an equal number of outside. So here we would measure 0. We would measure no net difference in charge. Now, let's imagine that we could magically take some of the positive charges from the inside of the cell and place them outside of the cell. What do you imagine we would measure now? Well, hopefully you'd remember that we would measure a net negative voltage, meaning that the inside has a greater accumulation of negative charge compared to the outside. And this is in fact what we see in neurons. Now, what would you imagine would happen if we just sort of suddenly opened a hole in the membrane of the cell and now sort of made the inside and the outside of the cell be continuous with one another? Well, hopefully you'll remember that charged particles, ions, that have dissimilar charges attract one another. And because the inside of the cell here has a net negative charge, it's going to attract these positively charged ions inside of the cell. And if you wait long enough, there will be a net movement of positive charges from the outside of the cell to the inside of the cell until the net distribution of charge is the same, both inside and outside, meaning that we would be back to where we started with a net 0 voltage difference between the inside and the outside. So, hopefully, this sort of little toy example, this little thought experiment makes sense to you. If not, go back and maybe review these parts of the lecture. And of course, you can ask me about it on Monday when we meet in person. Now, one last thing here, just to make sure that we're all using the right terminology for this. There's a particular word we use when a substance moves from a region of higher concentration to lower concentration. And that word is diffusion. And diffusion can apply to any substance that's moving from an area of high to low concentration. You should also remember that there's also a special word we use when it's not just any old substance that's moving, but when charged particles are moving or are flowing through a medium from one place to another. Hopefully you should remember we call that current. Now, this may be a little unusual. Normally we think of current as something that flows over electrical wires. But when we have charged particles moving in cells and in biological systems, that is also called current. Okay, here's a summary of what we talked about today. I'm looking forward to finishing up the video with the next one soon, and then I'll see you guys on Monday. Take care.